Testing on YouTube. Testing on YouTube. Testing on YouTube. All right. YouTube seems to work. All right, just one more left here. Just got to do X. How's it going, Josh Phillips? Should probably figure out a way to put the chat on the actual screen. How's it going, Elevate Group? Hope you are doing well as well. Drinking some Yopon tea today. It's the only caffeinated plant in North America. How's it going, Majetti Gizzle? Appreciate the hype and support here. All right, I think we're getting started. Let's make sure it works on X. Seems like it's working, so let's go ahead and get started. All right, welcome to another Hoopo stream. Today we're going to be looking at Mixtral 8x7B SMoE, and hopefully by the end of this stream you know what all of those stand for. So this is going to be a couple different papers. I picked out 4 that I think kind of focus around this idea of MOEs, and then more specifically the Mixtral MOE. So maybe let's start with understanding what the hell this word is, right? So Mixtral, right, is another English word for basically like a bard, right? So bard, which is the name of the Google model, it's like comes from this concept of medieval Europe where you had these people that would go around and they would sing, and it was basically the musicians who were also the poets. So, you know, there's something there with creating songs and kind of the whole generative part of these generative language models. But basically this is a language model created by a company called Mixtral. This is the company. It's in France, relatively small company. They pretty much put all their names in the title. So you can see here, this is the paper for the original Mixtral 7B language model released on 10th October 2023. And this is kind of roughly their team size at that point. And then you can see how they've added a couple more people. And this is the most recent version in 8th January 2024. So why did they have this mix there? And that's also kind of a pun on words. So Mistral is the medieval kind of like songwriter, and then Mixtral comes from the fact that it's going to be a mixture of 7 Mistrals. So it's a mixture of experts model. That's where the SMoE comes. Sparse comes from the fact that only a subset of those experts are going to be used at any one time during inference. So Mixtral is basically a pun on that. And that's the etymology of Mixtral of experts. So we're going to start with this paper here, the Mixtral paper, because I think it's pretty good kind of like just summary, and then we'll kind of go into a couple different other papers. I particularly want to bring up this paper here, Fast Inference of Mixture of Experts Language Models with Offloading. Also relatively recent from 2 people coming from Yandex, which is I think the Russian Google as far as I understand. But this paper is actually quite good. I actually like this one the best out of all the 4 that I've pulled up, because they kind of really go into detail about all the different tricks that you need to actually run these locally. And if you're using Mixtral, right, the whole point of using these Mixtral and Mixtral models is that they're open source models and you can run them locally without the prying Orwellian eyes of the large tech companies. So let's start here with the abstract. we introduce Mixtral 8x7b, so the 8 is how many experts there are, and the 7b refers to the number of parameters, right? So it's basically 8 of these Mixtral 7b's. A sparse mixture of expert language model. Mixtral has the same architecture as Mixtral 7b, with a difference that each layer is composed of 8 feed-forward blocks, i.e. experts. For every token at each layer, a router network selects 2 experts to process the current state and combine their output. So I think, why don't we just finish this, and then we'll kind of go in detail into what a router is and kind of, well, the feed-forward blocks and all of that. Even though each token only sees 2 experts, the selected experts can be different at each time step. And this is kind of part of the Achilles heel of these mixture of expert models, is that because they have to have basically all 8 experts ready to go at any moment in time, like token to token, it can lead to a lot of performance issues, especially if you're doing just one kind of single token inference rather than kind of batched inference, which is, I think, what these were originally designed for. As a result, each token has access to 47 billion parameters, but only uses 13 billion active parameters during inference. So what it means is that because these routers basically pick a subset of the experts at every feed-forward block, you're not going to be using all of the model parameters. So you're only going to be using some small subset of those, and they call these active parameters. Mistral was trained with a context size of 32K tokens, and it outperforms or matches Llama 270B and GPT 3.5. So this is the kind of 2 models that they want you to think about whenever you're kind of comparing the performance here. It's basically equivalent to Llama 270B and GPT 3.5, but note how they didn't say GPT 4 there. So they didn't quite beat the dethrone the king that is GPT 4. Mixtral vastly outperforms on mathematics, code generation, multilingual benchmarks. We also provide a model fine-tuned to follow instructions. So this is the instruction tuning, kind of like the chat type models. Mistral 8b7 or 8x7b instruct. That surpasses GPT 3.5, Turbo, Claude, Gemini Pro, Llama 2, and blah, blah, blah. Both of the base and instruct models are released under the Apache 2 license. The Apache 2 license, along with the MIT license, is basically the most permissive open source license. I think the Apache one is actually technically a little bit more permissive because it gives you some like patent protections as well or something like that. But generally MIT and Apache 2, you can effectively think of them as the same thing, and it's basically you can use these models for commercial purposes, research purposes, whatever you want to do. So there you go. That's Mistral. And how's it going? I don't know how to say your name, unfortunately. It says a Chinese name. Can you also review the code repo and tell us how the model is implemented in code? I don't have the code repo pulled up, but I will be going into this. So I'm going to be referring to this throughout the stream. This is a basically a visualization of a transformer architecture. This is specifically Nano GPT, just because it's small and it kind of fits in one screen. But I think it's a kind of very good visual tool to explain what's going on, and maybe we can just jump right into that, right? So here in figure 1, we have the mixture of experts layer. Each input vector is assigned to 2 of the 8 experts via router. So there's this little kind of component here that is a router that basically picks 2 of the 8 experts, and these experts are feed-forward blocks. So if we go to our LLM visualization, right, we have here at the very top, this is your input. So your input is composed of these tokens. Here in this simplified example, the tokens are basically just A, B, or C. Those tokens get turned into actual embeddings here, and then they get sent into this part here. So this part here is the attention block. So you see this multi-head causal self-attention right here. This is a standard kind of like block and arrow diagram, but then this is kind of a more nuanced diagram. So you can see here how there's kind of 3 heads. You see that? There's 3 of these. 3 heads, 3 sets of Q, K, and V matrices. Each one of these is a head, and that's your multi-head self-attention, right? So basically these tokens are paying attention to each other with multiple heads, so you get slightly different kind of behavior. But that's not the part where you have experts. The experts are the feed-forward block. So the experts are actually this part down here, right? So this is the feed-forward block. Here it's called the multi-layer perceptron, or MLP, but a feed-forward and multi-layer perceptron are kind of the same thing. And you see these are the weights inside that multi-layer perceptron, right, that encode basically the connectivity between these two linear layers here. And this is the part where you would actually have the experts. So if you can imagine 8 of these, 1, 2, 3, 4, 5, 6, 7, 8, kind of stacked right there, and then right before it over here, you would have a basically a router which picks 2 out of these 8. So that's what the mixture of experts is. It's basically just 8 of these feed-forward blocks, this blue block here, and then the router that picks from those. Okay, some stuff in the introduction here. So Mixtral allows faster inference speed at low batch sizes and higher throughput at large batch sizes. So the faster inference speed at low batch sizes, this is kind of not actually entirely true, right? If you're loading this model on your GPU at home and you're kind of interacting it with a batch size of kind of 1, right, where you're basically saying there's only one person doing inference at a time, it's just me on my computer, it is going to be slower than other models because it has to be loading these experts, right? The experts don't necessarily all fit on your GPU, so they're going to be kind of like loaded, and it can be very slow. But these models are very good at high throughput at large batch sizes, and these large batch sizes corresponds to if you're doing inference in a kind of a cloud environment and you have a product and there's like hundreds of inference requests coming in from hundreds of users all over the world, being able to batch those and then feed them in is actually going to be allow for higher throughput, because it also means that different experts, different requests, different inference requests from different users will be routed through slightly different experts. So all of the experts are kind of being used. But we'll go into that more when we look at this paper here, because this paper here really nicely talks about that. What else? We got context size of 32K tokens. The layer's output is the weighted sum of the outputs of the 2 selected experts. So there's nothing fancy that happens once you kind of like feed what comes out of the multi-head attention into the this MLP or the feed forward block, right? Both of the it's going to go through 2 specific experts, but then those are just going to literally just get added, right? Which is actually what happens normally, right? Because if you actually look at a transformer architecture, you have these residual connections. So here you see this residual connection. Usually the residual connection is kind of shown as kind of an arrow that goes around. So you see here's what the residual connection looks like in the kind of block and arrow diagram. It's this little arrow that goes like this and goes around and then gets added to the output. So it kind of like skips. Skip connection is another name for these. But here in this diagram, they kind of show it as a vertical line that goes all the way down. And you can see here how the multi-head attention goes out, does all this computation here, and then it basically gets added back to here. So here, this visualization is kind of interesting because it makes you kind of realize that residual connections are kind of like a straight path that goes all the way through to the bottom where the output is, right? So kind of similar to that here, where you have the output of the feed forward or the MLP just getting added to this like straight down line, which is the residual connections or that path, right? The same thing is happening with these routers, where they're basically just the output of these experts is just getting added together and then added to whatever other crap is coming out of that self-attention. Okay. So the Mistral 8x7b instruct is just fine-tuned on chat conversations. I couldn't actually find a lot of detail about the data. So this was actually something that was a little bit lame, I guess, about the Mixtral and the Mistral paper, which is the smaller one, is that, they release the models under Apache 2. They give you the weights and the code so you can do it all yourself locally. But they don't really tell you what they trained it on. They kind of just vaguely mention, oh, we're using open source data sets, but like in neither of these papers do they go into a very detailed explanation of like how they clean the data or what specific mix of data they used, or if they used any kind of techniques or kind of secret sauce to like kind of augment certain parts of the data. I feel like the data is really kind of the most important part, so it's a little bit lame that neither of these papers really explains that to you. I thought that was a little bit suspicious. Okay, so both of these models are released under Apache 2, and then they tell you their stack, which is interesting. So they're using VLLM and then also SkyPilot. So VLLM and SkyPilot. VLLM here is the GitHub repo for it, also Apache 2 license. It's easy, fast, and cheap LLM serving for everyone. So this creates basically LLM servers that you can ping. So whenever you're using language models through an API, this is what you're basically calling something that is serving that LLM to you. So you can see it's relatively active. They're still pushing updates here. If we look at the commits, you got last month, you got last week. So people are definitely using this. It's mostly Python code here, so you can see that. But here in the About section, it's state-of-the-art serving throughput, efficient management of attention, key, and value memory with page attention. These are the kind of like fancy KV caches. Continuous batching of incoming requests. So this is kind of what I was referring to before, where when you have a LLM server that's sitting there and you have hundreds of users all over the world pinging your API, those requests, you want to kind of batch them intelligently. And that's what this VLLM is going to do, some of that for you. And of course, any language model that's implemented in a Python framework like PyTorch or JAX or TensorFlow, that's not actually what's running, right? What's actually running on the computer are these CUDA kernels. So, of course, they're going to use all the cool kid CUDA kernels that are the best. So that's basically it. You can see here, look at all these different models that they support. So that's VLLM. And then SkyPilot, this is the other kind of part of their infrastructure stack that they use. SkyPilot is more kind of on the orchestration end. So this seems to be kind of like jobs and queues, kind of like a Kubernetes type situation. So SkyPilot is a framework for running LLM AI and batch jobs on the cloud, abstracts away cloud infra burdens. So easy scale out, queue and run many jobs, easy access to object stores. So object stores such as S3, this is where you're going to actually be keeping your data, right? Or maybe specific other assets that your pipeline might need. I think in a language model, you probably don't need very much because it's already kind of loaded on there. But if you were doing other types of workloads, maybe you need to load specific, I don't know, images, 3D stuff, different LoRa's. But it seems like the biggest advantage of this is it basically abstracts away a bunch of the crap in AWS, Google Cloud, and Kubernetes, and it kind of offers it to you in one higher level abstraction, which could be convenient, but I don't know, a lot of these are pretty bad to begin with. You know, like AWS, Google Cloud, like Azure, these clouds are kind of notorious for having abstractions on abstractions on abstractions that have been building this like spaghetti code for the past like 10 years, and they're very annoying and complicated to deal with. Unfortunately, a lot of people want the ability to switch between cloud providers, right? If you're a startup, you don't want to be kind of pegged to a single cloud provider because that could really cause problems if they increase the prices. You want to be able to kind of like flexibly switch between those. So SkyPilot is one of these solutions that basically tries to create yet another abstraction at a higher level that allows you to kind of easily switch between these cloud providers. So I thought that was cool. You know, they don't tell you what data sets they use, but they tell you their kind of stack that they use to serve the language models. I wonder if they got paid for this, right? Because think about how many people are going to be reading this paper, and then how many people who are doing their own startups are going to be like, oh, well, I don't know what to use. I might as well just use what the people at Mixtral use because they seem to know what they're doing. So I'm going to use VLLM and SkyPilot. So I wonder if they paid for that placement. I wonder if we're seeing the beginning of paid placement in papers. All right, you guys got some question in here. I want to build a server for trying out these LLMs. Is 2 Tesla P40s 24? Yeah, that seems definitely more than enough. But I wouldn't build a server because it's cheaper. It's honestly going to be more expensive to build a server, Mishra. You better off just, if you just want to mess around, just use kind of cloud service providers, and they have all kinds of free tiers, and they'll give you free credits. Can you explain the process for how a router network would choose what experts to use? Yeah, that's going to be this part here, so we're going to go into that. Server running, fairly happy. When you say routed and added through, can you give some intuition as to why? So the adding is already happening. So the adding isn't like new, right? So the adding is happening here. You see this green arrow here where basically all the output of this part here, the MLP, the feed forward block, just gets added here, the residual connection. That corresponds to this arrow here, like this, that gets added there. So that's really what they mean by the adding, is they're basically just adding it back to this kind of residual pathway. But that's happening anyways, right? That's exactly what happens with these this attention block right here, multi-head attention. You're just adding it back to the attention residual, as they call it here, MLP residual. But it just looks weird because normally if you're used to looking at these kind of block diagrams, it feels like the main path is like straight through all these blocks, but you forget that there's actually a path that goes like this that's basically unaltered. It just kind of, you're not used to looking at it this way where it looks like it's the main path, but it's just a straight line down. Okay. So only the feed-forward blocks are replaced by mixture of expert layers, and here they go into the actual what a sparse mixture of experts is. So the output of an MoE module for a given input X is going to be a sequence of tokens, right? So basically just an ordered sequence of little vectors that represent tokens. The weighted sum of the outputs of the expert network, where the weights are given by the gating network's output. So the gating network is another name for this router. And there's all kinds of routers, right? There's, I kind of remember capsule networks had this idea of a router too. They use that same word, router. Capsule networks are like this ancient type of network that was supposed to beat ConvNets, but it never ended up being popular. But like this idea of routers and gating is not necessarily new. So you have n of these expert networks, which right are just basically different feed-forward blocks, and you have n of them. So here you have a set from 0 all the way to n-1, 0 indexed. And g of x is the output of the gating network. So basically the output is going to be the sum from 0 to basically all of the experts of g of xi times e of xi, which is the output of the specific expert. So you're feeding the input x into the expert. You're getting some output, and that's the output of that specific expert. And then the gxi is basically gxi is the n-dimensional output of the gating network for the xi, or for the ith expert. Gx without the sub index, what is that called? Subscript. Gx without the subscript is the combination of those. So you're going to have basically 8 of these, right? And the problem is a lot of those are going to be 0, right? So if the gating vector is sparse, we can avoid computing the output of the experts whose gates are 0, right? So the whole point is that ideally you don't want to basically compute e of I x for every single expert, right? You only want to do it for some subset. If you had to feed in x here and compute this term here for every single expert, that would just be expensive as fuck, and it would just be a 47 billion parameter model, right? The whole point is that you're skipping a bunch of these. So what they're going to look at is they're going to feed that input x into this gating network, and then that gating network is basically going to say most of these are going to be 0, except there's going to be 2 of them that are going to be higher than all the rest, right? And the way that you know that it's higher is basically this top k logits of the linear layer. So the gating network is effectively picking the top one of those, and then you only basically calculate the expert path through those 2. So it saves you the cost of having to do 6 other expert inferences here. Does that kind of make sense, Majetti? Maybe? There are multiple alternative ways, but a simple and performant one is implemented by taking the softmax over the top k logits. So the softmax just basically takes the logits, which are just going to be some number from -infinity to infinity, and then squashes them into that 0 to 1 so that can be interpreted as a kind of a probability. The value of k, the number of experts used per token, is a hyperparameter that modulates the amount of compute used to process each token. So this is kind of interesting too, because it means that you can kind of crank up this k. In the paper, they always use 2, but you could have a k of 3, 4, 5, or 6, right? Like you can keep increasing this k, and you would probably see like kind of an increase in performance, right? I bet you if you have a k equals 8, it's going to be much slower for inference, but I bet you the performance is higher. One can increase the model's parameter count while keeping its computational cost effectively constant. This is not true either, and we'll see in that other paper why. This motivates the distinction between a model's total parameter count, commonly referred to as the sparse parameter count, and I don't like this word either, because sparsity has a bunch of other definitions. To me, when you use the word sparse, it usually refers to like a specific family of techniques that are dealing with reducing the total parameter count of a neural network, right? So when you're trying to prune a model, right, you make it more sparse. But here they're basically kind of overloading that terminology and saying that the sparse parameter count is all of the parameters put together, and then the active parameter count is only the parameters that you use in basically one inference pass for a single token. MoE layers run efficiently. Different experts get a variable number of tokens assigned to them, right? So you don't know beforehand which experts are going to get the input, right? You have to basically run the input through this gating network, and then do the top K of those. And so you don't know, and basically until the very, very last moment, which actual expert you're going to use. And that ends up being a problem, right? So they bring it up. I keep mentioning this other paper. Maybe I should just jump right to it. But let you feed your input, right? You're feeding your input. Ooh. It comes in through here. It goes in through the multi-head self-attention. It goes down here. And then it's going to go into the gating network basically right here, right? And the gating network, assume there's basically 8 of these. So this is just one feed forward, but imagine 8 of these kind of in parallel, similar to kind of these this multi-head attention setup here. The gating network is going to basically pick which 2 of the 8 to actually perform the inference through, right? So that's an issue, because you basically have to wait until the very last moment to pick those 8. So you can't do anything kind of fancy where you know exactly which experts are going to be used and you can preload them onto the GPU and so on, right? You basically have to wait until the last moment. The MoE layer can be distributed to multi-GPUs and through a particular kind of partitioning strategy called expert parallelism. This is more kind of the way they're intended to be used, right? In this kind of like batched serving mode. And they call this expert parallelism, where you might have different experts on different GPUs. So even you have 8 of these, but then, I don't know, 4 of them are on one GPU, and then 4 of them are on a different GPU. In these kind of multi-GPU node kind of server racks, for example. And there's probably something there, right? Why do they have 8 experts? Well, probably because most server racks are made with 8 GPUs in them, right? So there's definitely some correspondence there between those two numbers. Tokens meant to be processed are routed to the specific GPU, and the expert's output is returned to the original token location. Note that EP introduces challenges in load balancing, right? So here the problem is going to be that because you don't know which expert to route it to, you might have one expert that receives a lot more, kind of a larger batch size than the other one. So this load balancing is kind of a whole can of worms that gets opened with this mixture of expert stuff that it seems like it's worth it, but I don't know. It's also just kind of adds a whole level of complexity that might not be worth it. I don't know. So the routing boils down to calculation of the largest values that arise from the 2 experts. Yeah, basically. You can think of this little gating network as basically like a little classification model, right? It basically picks which of the experts to use, right? So you see this WG, these are the weights of the gating network. So you can think of it basically just like a little tiny, it's not even an MLP, it's just like a little tiny neural net, little tiny layer that all it does is it basically just says, okay, here's all the input sequence X, and then the output is just going to be 8 numbers, and those 8 numbers, which are the logits, are going to correspond to basically like the classification, or like basically very similar to kind of the way you pick a token at the very end, right? You're basically saying which of these 8 little numbers that are in my little gating network, which of those has the highest value corresponding to the fact that that's the expert I should pick. No problem, man. I love explaining things. Okay. The MoE layer is applied independently per token, replaces the feed forward block. We use the same Swigglue architecture, blah, blah, blah. Taking all this together, the output Y for a token X is computed as blah. So this is basically just the raw output, which is at the very bottom of the network. X is the sequence, and then you have basically these bricks over and over again. Okay, so that's kind of the main meat of it. Like, there's not much to it, really. All they're taking is this Mixtral 7B, and then they're basically just exploding the feed-forward brick, making 8 of these, and then just adding this little layer, or this little gating network, which basically just chooses which of those 8 to use. And the reason people do this is because it performs pretty well, and then it also has the kind of benefits that you can kind of distribute it with this expert parallelism over a kind of like an 8-node GPU server cluster. So how much better is it, right? And here in figure 2, this is basically, they're trying to show off how good it is. Here they're comparing to Llama 2 7B, which is the small llama. That's this kind of like darker blue. Llama 2 13B, which is this one here. Llama 2 70B. This is kind of weird. They put the Llama 1 34B because the Llama 2 paper never had, they never released the 34B. I think eventually they might have released it, but I remember when we were reading it, the 34B wasn't there. So you can see that it's better than Mixtral 7B, so the yellow line is pretty much always bigger than this orange line, so it's better than just the 7B model by itself, but it's also more compute intensive, right? So of course it makes sense, it's like 8 times, but kind of what I see when I look at here is that it's pretty much always better than Llama, right? Llama 2 70B, look at that, it's like the yellow line is pretty much always higher, except for here comprehension and AGI eval. But it does really well in math and really well in code, which is kind of what they say this like 50 times in this paper, but superior in mathematics and code generation. Okay. Mixtral with Llama results on MMLU. This is basically just that bar chart, but just in line mode. It's a slightly different type of chart, but it's the same data. We compare performance. This analysis focuses on the active parameter count, which is directly proportional to the inference compute cost, but does not consider the memory cost and hardware utilization, which is a big problem with this. The memory costs for serving Mixtral are proportional to its sparse parameter count, which is still smaller. As for device utilization, we note that SMoE layers introduce additional overhead due to the routing mechanism due to the increased memory loads when running more than one expert per device, right? And this is probably a good time to go into this paper, which I found very useful. So this is fast inference of mixture of experts language models with offloading. Many deep learning practitioners looking for strategies. One such strategy is to use sparse mixture of experts, a type of model architecture where only a fraction of the model layers are active for any given input, right? So this is only a subset of those experts are used for an inference pass. This property allows MoE-based language models to generate tokens faster than their dense counterparts. And I kind of like the fact that they put this in quotation marks because they're starting to redefine what dense and sparse means. Like I said before, those have different definitions in my head, dealing more with like literally the weight matrices themselves. Are they sparse? Are they dense? But here they're referring to the fact that in mixture of experts model, only a subset of all the weights are used. But also increases the model size due to having multiple experts. Unfortunately, this makes state-of-the-art MoE language models difficult to run without high-end GPUs. We studied the problem of running large MoE on consumer hardware with limited accelerator memory. So they're basically going to be running this on GPUs at home. And this is the different GPUs they consider on. So they have a free tier Colab instance with a T4 GPU. This is the TPUs. They have, this is NVIDIA. I'm not exactly sure. Is the T4 reference the TPU or the IDK? But this RTX 3080 and this RTX 3060, those are kind of consumer GPUs that you might have at home with 12 gigabytes of VRAM and 16 gigabytes of VRAM. We run mixed quantization on desktop hardware and free tier Google Colab instances. So the mixed quantization here refers to, in this paper, they're going to be quantizing it, but different parts at different levels of quantization. So quantization is a technique which has gotten really popular due to these Tim Detmer's papers, which we've reviewed on the channel as well. But basically, they're reducing the precision of the data types for each of the parameters in these models, and you can drastically reduce the total memory used for a model by quantization. And there's different levels of quantization, so you can have 16-bit, 8-bit, 4-bit, 2-bit and even down to like 1-bit. But obviously, as you go down, the performance kind of starts to go to shit. So you kind of want to quantize it as much as possible. And then if you're really fancy, which is what they do in this paper, they quantize different parts of it at different levels. So I think they describe it somewhere over here, but they end up with basically, yeah, so we choose 4-bit quantization for the shared attention layers. So they're going to quantize this part of it here. The multi-head attention is going to be 4-bit quantization, but then the 2-bit or 3-bit quantization for the experts. So then for these experts here, right, the experts here, and imagine that there's 8 of these, right? Imagine that there's 1, 2, 3, 4, 5, 6, 7, 8, kind of similar to the multi-head attention. They're going to quantize these at 2-bit. So that's that kind of like mixed precision quantization. Seems like a neat little trick that people could be using with these mixture of expert models. Okay, but let's go a little bit further into this paper. MoE language models builds on a relatively old idea. Here's the OG papers, 1991, 1994, where apparently people had a mixture of experts. They simultaneously train the gating function. The gating function is the routing network to choose the best experts. And 2, training the experts themselves on samples assigned to them by the gating function. So basically you're training this gating function, or you're training a router network, which is approximating this gating function, right? A network is just a function approximator. And you're training that router at the same time as you're training the actual experts themselves. Many different MoE variants have emerged. Something interesting here that when they're training these MoE models, you have to basically add additional regularization to promote equal expert utilization, right? Like this makes a ton of sense. It's kind of like similar to something like dropout, right? Where one of the core ideas behind dropout, which is a type of regularization where you basically drop out or kind of zero out certain neurons within a neural network. Part of that was because if you don't do that type of regularization, the kind of model will kind of start to over-rely on one specific path, and then it'll kind of just ignore everything else, right? So you can imagine a similar thing kind of happening here with these mixture of experts, where one expert would end up kind of like getting ahead of the pack, and then over time, the router would just always choose that expert. So you have to have some kind of regularization that kind of like forces every single expert to be used somewhat more equally. And I think that this might be the reason for some of the weirdness that you see. So back to the Mixtral paper. In the Mixtral paper, they have a section here where they analyze which experts are used. So we do not observe obvious patterns in the assignment of experts. And this is very interesting because naively, right, when you think about mixture of experts, I, in my head at least, was thinking, okay, so there's probably an expert in English and French and blah, 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 or there's probably kind of like a coding expert, and there's probably a poetry expert, but that's not actually what you see at all, right? And it actually turns out that the experts are like very strange, right? It's not easy to interpret what the fuck is going on as a human. So they do say that you're getting a marginally different distribution of experts based on the task, but it's not like the expert is kind of like task specific. It's almost more token specific. So here they have, where is it? Right here. So here they have text. This is figure 8. Text samples where each token is colored with the first expert choice. Okay, so you see here the color represent which expert was chosen for that particular token. And remember that the expert is chosen every single time. So a autoregressive language model, right? It's basically picking, it's going through and performing inference like this, right? For every token. So every time you want to predict the next token here, right, you have to basically do this entire fucking thing. So you don't, obviously parts of this are cached, right? Your KV cache, you're not going to have to recompute everything. There's fancy ways of not having to recompute everything. But in an MoE, right, you don't know which expert to use until you actually get to here, right? Because the gating network is using this information here to pick one of these experts. So that's what's going on here, right? You can see how every single token, and here you can actually see that the word self is one token, the word super is one token, this like parentheses with a dot is a token, right? But look at the specific choice of experts that they're picking. It's very weird, right? Like, there's obviously one expert, this red expert loves like the indents, but then here, like, look at this here. Like, why is this expert is picking the open parentheses, and then a different expert is picking the closed parentheses? You have one expert picking this dot here, and then you have a different expert picking this dot here, right? Like, that's fucking weird, right? Layer 0, the same expert picks the dot for all of these, but then layer 15, you have different experts picking different dots. Shit's weird. But, you know, it's not like completely unusual, right? Because we're kind of used to this, right? We moved away from the world of kind of hand-designed features where humans would design these features, especially in computer vision, and the hand-designed computer vision features, they were very understandable, right? You could look at a histogram of gradients or like a SIFT feed. You can understand that as a human of what exactly is going on. But now that we've moved into this kind of like deep learning paradigm where kind of the models pick for you, right? Everything has become much harder to interpret, much more black box. So it's kind of par for the course that you create this mixture of experts model, you train it, you have some regularization that forces the usage of all the different experts equally, and you end up in this weird situation where the mixture of experts works better, but it's not entirely clear what each expert's even really doing, and it's kind of strange. I don't know. Let's see. T4 is an NVIDIA GPU. Yeah, that's what I thought. Every time I see the T, I feel like I get confused and I think it's a TPU, but there is an NVIDIA GPU called a T4. Let's see, NVIDIA T4. Yeah, this one here. This is kind of an old GPU, to be honest. They probably stopped using the letter T just because Google has the letter T. Okay, back to this one here. So we're back to this Russian paper where you have these two guys that were basically trying to get a mixture of experts model to run on consumer hardware. So they're here, they're talking about mixture of experts, they're talking about quantization, so post-training quantization, right? You can do quantization that's aware of the training, that's called training-aware quantization. There's a lot of different types of quantization that you can get increasingly fancy, more fancy, less fancy, but kind of you can just basically think of it like you're trading precision for memory is basically the trade-off there. Is you're basically compressing these weights, making them more fuzzy, less precise, less bits being used to actually store that weight, but the trade-off is that it's going to be more kind of noisy and eventually lead to less performance. 4 bits is kind of like the go-to kind of Goldilocks amount of quantization, but they mention here that people have gone as low as 3 and 2, and I think we even read a paper on the channel that was like 1-bit quantization, so kind of crazy shit. All right, inference with parameter offloading. This is kind of the more interesting section here. A recent line of work with limited accelerator memory by offloading the parameters to another cheaper memory such as RAM or even SSD. So the RAM is sometimes people call this the CPU memory, but it's basically the memory that kind of your normal computer has, and your CPU can put things on the RAM, take things off the RAM, but the RAM is different from the VRAM, right? The VRAM, or the video RAM, is the memory that's actually on the GPU. And the important thing to remember with memory here is that the closer it is to the actual thing doing the matrix multiply, right, the actual GPU core, the faster it's going to be to load it on, do the multiplication, do whatever you need to do, and then load it off, right? So the further away you get from that GPU core, the longer it's going to take to load. So if you can have things in the VRAM, that's going to be much, much faster than if you have to go to the RAM. Now you have to wait for the CPU to load it and put it onto the GPU, go through that PCIe, which is the name of kind of it's the name of the slot where you plug in your GPU, but it's also kind of the kind of like communication standard for that, right? So For example, here, PCIe Gen 3. So the worse than that would be the SSD. The SSD would basically be the cold storage. At that point, you're literally like loading it from a disk, although nowadays it's not really a SSD anymore. Usually it's the same kind of memory that you have in your RAM, but it's still slower than the RAM. This technique works by loading model parameters just in time when they are needed for computation. Since most deep learning models use layers in a fixed order, offloading can pre-dispatch the next layer parameter in the background ahead of time. This technique works particularly well when processing large batches of data during training. In turn, when doing interactive inference, offloading works significantly slower than on-device inference. This is because interactive inference generates tokens autoregressively from left to right, right? You're generating those tokens one at a time, and you can't generate the next token until you have the current token. So it's not like you can kind of generate a whole string of them. There are techniques that try to kind of game this. There's the technique that people have started doing called speculative decoding, where you kind of speculate on what future tokens are going to be given kind of your current token, and then you can kind of basically do inference with a little bit of a look ahead, except it's not, you're going to have to check your work, right? Because it could be the case that the next token that comes out actually invalidates that kind of speculative guess that you made ahead of yourself. Inference system proposes a few tokens and therefore spends most of the time waiting for the next layer's parameters to be loaded. Okay, so they're going to do this on some small consumer GPUs and free tier cloud instances. So basically they're trying to pick systems that have a small amount of VRAM. 16 gigs of VRAM is not going to be enough to fit the 70B Llama model or the full, all the active weights of this MoE, which I think is like 47B. Yeah, you're not going to be able to fit that on your VRAM. So, method. We systematically find the optimal way to inference modern mixture of experts on desktop or low-end cloud instances. Consists of two phases, encoding the input prompt and generating tokens conditioned on that prompt. The key difference between these two phases is that the prompt tokens are encoded in parallel, whereas the generation runs sequentially. So here they're talking about, in these language models, you'll have an encoding part, and then you'll have the decoding part. So the encoding part is the part that consumes your prompt. And because your prompt is written and you hit enter and that whole prompt is available, you can basically do that all in parallel. So the encoding is actually quite fast. It's the decoding, which is the actual little generation, that is slow, right? So whenever you're using any of these GPT or Perplexity things, it's like you can see how it kind of like produces your output token by token, and that's the part that's small, or that's slow. Phase 1 works relatively well since each layer can be loaded once. In turn, when generating tokens, one must load a layer once per each token generated. This means that inference speed is limited by how fast one can fetch parameters from the system memory, right? So this is kind of the problem that we were talking about, right? Where because you don't actually know which of the 8 experts you're going to be using until you actually go and get that token and feed it through this whole attention block, and then come here and feed it through your router network, and then the router network tells you, okay, the two highest values, the two experts that I want to use are expert number 3 and expert number 7. So now, if you're using a shitty GPU at home and you don't even have those experts loaded on your VRAM, now you have to wait, because you're going to have to go to the CPU and say, hey, can you load the parameters for expert 3 and expert 7? And the CPU will be like, okay, let me go to the RAM, and I'm going to grab those, and I'm going to put them on the VRAM, and then the GPU is going to be like, okay, now I have expert 3 and expert 7. Let me actually calculate. Let me feed that in there. Boom, boom, boom. Add them together, and then boom, now I'm at the next one. And then guess what? You're going to have to do that again, because then you're going to feed that output into the next block, right? And you're going to have a bunch of these transformer blocks over and over and over again, and you're going to have to wait until right here, right until you get to the next router network, which is going to be like, okay, actually, now I want you to load expert 4, and I want you to load expert 1, and then you're going to have to go back to the CPU is going to go to the RAM is going to send it back to the VRAM, and so on. So it's like, that's just the kryptonite of these mixture of expert models, that if you don't have the GPU VRAM to load all of the experts, you're basically going to have to be constantly waiting for the CPU to load the expert required for every single attention block for every single token as you autoregressively produce it token by token. So not a good situation, you know? that's not a good... these MoE models are not intended to be run on single consumer GPUs, right? A lot of the magic of these comes whenever you're doing these kind of like batched cloud workflows, because you don't need to load every single model at every time, right? Because you have a server cluster that has 8 nodes in it, and each GPU in each of those 8 nodes has one of the experts in it. So at that point, you don't need to go to the CPU to then load expert number 4. You can basically say, okay, well, actually, this time I need to use expert number 4. Let me send this information to GPU number 4, which has that 4th expert loaded, right? So these MoEs are really, they're designed for these kind of batched cloud inference workloads. Okay. SSD is still slower. What was the 3D done with? I don't know. This website, by the way, is so good. Like, I'm just kind of like going like this, but I highly recommend everyone here to go through this once. Like, you basically go through this, and then they have like little animations. I'm just not going through the animations, but like, look how nice this is, right? It's like they basically, it's so cool. I don't know who did this. I should probably give this person credit. It is on the notes, but like, it's so pretty. Look at that. Look at that. Boom, boom, boom. It's adding the token embedding. Here's the position embedding, right? So you can see how there's a different vector here for every single one of the possible positions in this sequence. So here you have a sequence of tokens, right? And this first one here corresponds to the position embedding for the first place, and this one here corresponds to the position embedding for the second place, and so on, right? So there's just so much cool shit here. I really recommend this little visualization, and I can't believe I think I found this earlier, but I just never really like realized how cool it was. Okay. Expert locality and LRU caching. Caching comes from the French word cacher, which means to hide, right? And a cache is basically a place where you keep things that you might need again, right? So in this case, caching, when it's referred to in the kind of like a programming context, refers to this idea of like, hey, I'm going to keep these things here in this little memory location, not because I need them right now, but because I might need them in the future, right? And I don't want to have to go and maybe recalculate them, or have to go to a shittier, a further away memory place like the SSD to go grab these. Let me keep these like close to me at hand, right? So LRU caching, I think specifically stands for like last recently used, something like that, or least recently used. But it basically is like a cache that's kind of like ordered in a way that where the things that you tend to go and reuse again are kept, and then the things that kind of you use once and you used it like a long time ago, that'll be the one that gets overwritten. So it's kind of like a way of keeping like a kind of a hot cache. Okay. Mixture of expert language models often observed to assign individual experts to distinct subtasks, but that is not the case. However, this does not mean that the model uses the same expert over long stretches of token, which we know for a fact, right? If we go back to this paper here, that's not the case at all, right? It's basically the expert is changing almost token by token. You do have some little sequences right here. You have basically 3 tokens that use the same expert. Here you have 3 tokens that use the same expert, but like most of the time, you're actually changing the expert almost token by token. Some experts are active in short sequences, while others are often used with gaps. To take advantage of this pattern, we keep active experts in GPU memory, right, this VRAM, as a cache for future tokens. If the same experts are activated again, they will be available instantaneously. Naturally, the number of experts can be stored this way if is very limited. Here's a little typo. Let me do red. Red is my typo color. The number of experts that can be stored this way is very limited by the available GPU memory, right? If you can fit all of your 8 experts in your GPU VRAM, then you don't give a shit about any of this, right? You're fine. You can just run it in, and like a lot of the parameters are kind of not necessarily doing much, but it's totally fine. The problem is if you want to run this on a GPU that doesn't have enough memory to load all the experts in it, right? And there's a bunch of them, right? We choose to always keep the K least recently used experts. So here's your LRU cache, is basically you're keeping the most recently used ones. The cache will save experts from multiple previous tokens. We illustrate an example. LRU is a very simple strategy that does not consider factors like expert activation frequencies, varying cache size, or any sequential patterns in expert activation. So here they're more just kind of saying that LRU cache is kind of like the simplest version of that, but there's probably going to be more juice that you could squeeze out of this if you could somehow figure out some relationships between these, right? There's probably situations where if you know that you're using a certain type of expert here, you can kind of like predict that the next expert's going to be this one, right? There's probably relationships here. There's probably some signal in this noise, some pattern here that you could exploit to more efficiently kind of like load experts in and out of this cache, right? So expert activation frequency doesn't refer to like the activation of the neurons inside the expert or anything like that. It literally refers to like how often are you using this expert. All right, so if you remember, I brought up speculative decoding. So now we have speculative expert loading. So speculative expert loading is going to be when you speculatively load the experts that you think you're likely going to be using on the next token. Most of the inference time is still spent waiting for the next expert to be loaded. The reason behind this is that unlike with dense models, MoE offloading cannot effectively overlap expert loading with computation. Let us zoom into the process of generating a single token. The full compute workload starts by embedding the previous token, then alternates between running self-attention and MLP, right? So alternates between running self-attention and MLP for each transformer block, right? So here's your transformer block, here's your self-attention, here's your MLP, here's your self-attention, here's your MLP, here's your self-attention, MLP, right? So here, this is a simple one. NanoGPT just has 3, but you can have a lot more of these transformer blocks, right? And the MLP is also the feed forward. So a little bit confusing. I'm using different terminology, but don't get lost. And right, the problem is that you're doing this, you're going through this entire thing for every single token, and you're having to basically pick experts right when you need them, right? Just in time. You can't really know beforehand. This architecture allows for efficient offloading. So in regular, they're calling dense models. Unfortunately, this schedule is no longer possible because MoE MLP layers choose which experts to load just in time for computation. The system cannot prefetch the next layer until it learns which experts should be loaded. While it's not possible to reliably prefetch the next set of experts, the system could still try to guess the likely next experts and load them speculatively, right? The speculative part of that speculative expert loading. If it guesses correctly, it will speed up the next layer. If not, it can always load the next expert later. So basically, before you even know what expert you want to pick, you're already sending information. You're already sending basically a request to the CPU to say, "Hey, go grab me expert number 4 from the RAM, the just computer RAM, because I think I'm going to need it for the next token, or the next 2 tokens or something like that," right? And this will work well if you have a situation where experts are repeated, right? So if you know that you loaded, or this yellow expert always happens after this blue expert, then as soon as you get that blue expert, you can go and find that yellow expert. But the more weird the pattern of these experts becomes, the harder it is to do this kind of speculative loading. So the speculative expert loading would have worked absolutely amazingly if each of the experts was like task specific, right? So if you had a coding expert and a French expert, as soon as you see the French tokens, you could be like, oh, okay, let me load the French expert because I bet you I'm going to need that. But because that's not the case, and because these experts are like some weird pattern that's hard to kind of understand as a human, this speculative expert loading is not going to be as good. But they have a trick. We found that it is possible to get an accurate guess of the next layer's expert by applying the next layer's gating function to the previous layer's hidden states, or more specifically to the same hidden states that are used by the MoE layer's gating function. So what does this mean? This heuristic relies on the fact that transformer layers are residual. Okay, so what it means is that, let's say you're here, right? You're here, you calculated the attention block, and you have your little gating network, your little router, it's right here. And your router is looking at this and it's saying, okay, I need experts 3 and 4. normally you would just then feed that into there, get the experts 3 and 4, produce the output there, feed that through this multi-head self-attention, come back down here, and then the router here would say, okay, now what is it? Okay, now I need experts 7 and 4 or 7 and 8, right? And each layer has different experts, so this is a repeating process. What they're saying is like, actually what you can do is you can take this here and then feed it into the router here. So that's technically not correct, right? Because technically this router here is going to have to operate on what comes out of this and then this, right? So this is going to add something to this residual, and then this is also going to add something to the residual. So the router is going to be, you're basically making it operate on a guess, and you're basically making a guess that this residual here is going to be kind of similar to this residual here. So if I feed this residual here into this router network here, I can have a pretty good guess as to what the experts are going to be. And most of the time, even after I add the stuff from this feed forward block here, and after I add the stuff from this multi-head attention block here, it ends up being kind of the same experts. So that's kind of a neat little trick where they basically leverage this, the fact that the residual isn't necessarily changing a ton as you go from layer to layer to layer to layer to layer, to basically prefetch the experts by assuming that that residual is kind of indicative of what the future residual is going to be when you feed it into this gating function or this router network. Gating function is the router network. This architecture introduces an inductive bias such that any layer's hidden states are a decent estimate of the next layer's hidden states. Okay. Damn, you guys are popping off. Can you do a video explaining the concept of Gaussian splatting? You should join tomorrow, man. We got a Gaussian splat stream tomorrow. We kind of have a backlog of Gaussian splat papers to review, so if you're interested in that, definitely join tomorrow. Folks are sleeping on Apple Silicon. Yeah, I agree with you on that, Joseph. I don't know why Apple doesn't make their own kind of like data center chip. Obviously, the M3s, the M2s, those chips are actually pretty good. Like, there's people who, like, I'm not part of that because I don't really have a Mac laptop right now, but there's people who are running all kinds of language models locally on their Mac laptops, and they seems to be doing pretty well. So from that, I'm like, okay, well, why don't you just take that little M3 chip, make it twice as big, so now it's like a nice, big, fat kind of like chip like that, and then make a kind of data center chip. Make it so you can put it in a data center. Like, why don't you do that? Doesn't that seem like incredibly obvious to do if you're Apple, is make like a data center sized chip that's based on the same kind of magic that you have in your little M3 chips for your laptops and your VR headsets and your iPhones, right? I don't know, maybe they're already going to be doing that, but I feel like that's a no-brainer. MoE quantization. Okay, so here they go into quantizing, right? We talk how they did basically different levels of quantization for the experts and the attention. So that's another way to squeeze a little bit more memory performance from this. The LRU cache is equal to the number of experts per layer, so they have k equals 4 for the size of the LRU cache, 4 experts, right? And remember, there's experts for each layer, so it's not like you just have one expert for the entire thing. That's pretty much most of this paper here. I just loved that section there where they kind of describe all the different stuff, but past that, all they do, this is just basically just a bunch of benchmarking where they sweep all over the hyperparameter space. They try different levels of quantization, different sizes of this LRU cache, different setups, right? So like, it's not just the VRAM and the RAM. It's also like the speed, right? Like the speed of like how fast is that PCIe, right? Is it like an older gen? PCIe Gen 4 is going to be much faster than PCIe Gen 3, right? So like, they try on kind of this kind of like heterogeneous sample of hardware to see which things matter, which things don't matter. But they do note here that both GPUs are still bottlenecked by the host-to-device bandwidth limited by the PCIe architecture. So kind of the TLDR of this work, which they mention here, is that most of the time is spent waiting to load the expert, most of the inference time is still spent waiting for the next expert to be loaded. And then if you go all the way to the bottom here, both GPUs are bottlenecked by the hosted device bandwidth limited by the PCIe architecture. So the bottleneck in this entire system is not your GPU core, right? It's not your CPU. It's not your total number of RAM. It's basically the fact that this PCIe Gen 3 is slow as shit. So there you go. I thought this paper was cool. Also look at this. This is a little Easter egg for you guys. But so this is the reference section, right? And this is kind of how reference sections have looked for millions of years, right? You basically just have your names, and then you have your title, and then you have the conference. But more and more with these language model papers, we're seeing kind of these like monstrous author lists, right? So like, look at that, boom, like massive author list. And what does that mean for papers? Well, some people are starting to do this, right? Where rather than putting the name of people like this, they're just starting to say the team of people, right? But another way of doing it is this. Look at this. This is the Gemini paper. Gemini family of highly capable. Look at, like, what the fuck? Like, it's literally like an entire page of just names. I don't know which one of these is better, you know, because on one side, like doing it like this, where you say the Mixtral AI team, that means you no longer have SEO for your name, right? So like if you're a researcher, you kind of live and die by your citations. So having your name like this appear in papers is important for you to kind of like be able to raise money and gain fame and so on. But so whenever you have just the name of the team like that, you kind of lose out on kind of like celebrating the people in the paper. But then there's kind of the other side of it, which is like this just seems kind of ridiculous, where you have like literally 200 people's names in a reference. So I don't know how we're gonna change, right? It seems to me like the format for citations needs to change, but I don't know. Papers are kind of slowly dying anyways. You know, I feel like papers as a format are kind of like disappearing. But, you know, that's what we do in this channel, is we celebrate the dying age of papers. Okay. Awesome, dude. Would those be considered a foundational model? I wonder if there's any use for MoE in computer vision. Probably. Like, you could probably do this for computer vision as well, right? Like, there's nothing sacred about this technique. You could probably train something with it. The problem with computer vision is that it's very, like, foundation models in computer vision are basically impossible to do as even a small research lab. Like, the amount of money and GPU time you need to, like, push the state of the art in computer vision is absolutely insane. Like, you can do like different types of papers, right? Like the Gaussian splats papers, a bunch of those Gaussian splat or LoRa or kind of diffusion papers. Like, some of those can be done by smaller teams or even individual researchers. But when you're talking about like basically pre-training VIT with an MoE, I just don't feel like anybody can even do that at their house. Like, it's going to basically be the people at Facebook are going to eventually do that and post a paper on it, but there's nothing that we can do. We can just, all we're going to do is just basically wait until somebody else does it and see what the performance difference is. Okay, what was I even talking about here? I think we were here. We were looking at expert parallelism. We were looking at their results. This analysis, we compare the performance, aiming to understand. Does not consider the memory cost. The memory cost of Mixtral are pretty high. They're more suitable for batched workloads. I think that's kind of where we left off. Let's look at this. MMLU, kind of on par. Yeah, I mean, it's not necessarily always the best. Look at that. GPT 3.5 is better there. This is significantly better on this. About on par with that. 25 shot? What the fuck, dude? 25 shot does not seem like a good eval. We significantly upsample the proportion of multilingual data during pre-training. Okay, so this is interesting. They tell you a little bit about their data mix, right? So they have a lot of English data, probably a lot of Chinese data, and then they basically just increase, or you could think of it like they kind of duplicate the French, German, Spanish, and Italian data so that there's more of it. I wonder if they have any kind of text-based augmentation to just prevent training on the same thing over and over again. But you're doing that anyways, right? If you have more than one epoch. More benchmarks. Here, active params, right? So they come up with this terminology that active params is how many params you actually use, and then sparse params is how many you have total. So Llama 2 70B has 70B, of course. Llama 1 33B has 33B, and then Mistral 8x7B has 13B instead of the 47B. But if you're constantly having to load these into your GPU memory, it's like really not 13B, right? It's like 47B, so we evaluated on passkey retrieval tasks, synthetic task designed to measure the ability to retrieve a passkey randomly inserted in a long prompt. I've seen these before, so you sometimes see these on Twitter where it's basically people will feed this very long jumble of words into the context length of a model, and then they'll try to basically see if it forgot a bunch of that, because what people started doing is the context length became the metric to kind of optimize. So people wanted to have bigger and bigger contexts, but the problem is that they started doing it by almost like losing the information in there. So even though they had a huge context, it really just didn't remember most of the context. So now people came up with this task where you can actually test it just to make sure that it's actually getting the all of the information in the context. It can pay attention to everything in the context, and it's not just kind of getting rid of all of it or forgetting it. Okay. Bias. Is it more or less biased? I don't know whether higher is better. Seems pretty much the same. All these scores are the same. What is it? Why is this score exactly the same? It's kind of suspicious. If you see the same score like that on a eval benchmark, it probably means there's something wrong with the benchmark. Right? It's kind of like tests at school. If you make a test and everybody gets the same grade, it means the test was trash, right? It's like the whole point of the test is to separate out so you can see who's doing well, who's doing badly. But if everybody gets the same score on a test, it means the test was bad. Instruction, fine-tuning. This is the ELO style benchmark where you have people basically compare A or B, and you can think of it kind of like a head-to-head. So in this kind of arena ELO rating, Mixtral doing pretty good, just behind the GPT-4 and then the Anthropic models. I suspect that GPT Turbo is also a mixture of expert. People have said this before. People were speculating on this like last year, but it makes a ton of sense, right? Because it works well, it has high performance, and then they also happen to have the exact type of like batched, like kind of inference workloads that MOEs are particularly good at. So it makes sense that something like GPT-4 is probably also, even GPT 3.5 is probably also some kind of a mixture of experts. But look at that. Proprietary Apache. It's the best one. Marginally different distribution of experts. I think we already went through this. Here's the different expert selection for different layers. So here you have expert 0 all the way to 8. And remember that there is, whenever you train this, right, you do have a regularization loss, that additional regularizers to promote equal expert utilization. So here you see that expert 0, you want all these bars basically to be the same. You want it to pick every expert roughly equally. You don't want something like this where there's basically one expert that's kind of dominating and the other ones basically never get picked. And here they're trying to see if it's true that different tasks, such as archive versus GitHub, result in different experts. But consider experts that are either selected. A breakdown of the proportion is done in each case. Can be seen. Another typo. In each case can be seen. I'm the typo god. All right, conclusion. In this paper, we introduced Mixtral 8x7b, the first mixture of experts network to reach a state-of-the-art performance among open source models. It's probably not true. There's probably plenty of papers, even like decades ago, that did something that looked like that, but let's not Schmidt-Huber about it. Mixtral 8x7b Instruct outperforms Claude, Gemini, GPT Turbo only because it uses 2 experts at each step, only uses 13b active parameters per tokens, while outperforming the previous best model using 70b parameters per token. We are making our trained and fine-tuned models publicly available. By sharing our models, we aim to facilitate the development of new techniques and applications that could benefit a wide range of industries and domains. Okay. I think there's one more thing that I wanted to talk about today, and that's this. Let me sip this. Blowing my mind with that tangent on vision. I don't know, man. I feel like that was a terrible tangent. Okay, so we spent this entire stream kind of talking about the Mixtral of experts, specifically for the Mistral models, but I also wanted to think about how MoE works with different models. So this paper, which is also really recent, 8 January 2024, MoE Mamba, Efficient Selective State Space Models with Mixture of Experts. So Mamba is the name of a selective state space model, which is basically kind of like an RNN and a CNN kind of together. It's a new type of architecture, kind of similar, like it's supposed to compete with transformers. They released a paper, there was a little bit of hype, it kind of died down. Now you're seeing a little bit more papers come up. So far, it doesn't necessarily seem like it's going to be the transformer killer. I don't think people at OpenAI are using the Mamba architecture. I don't know if people are actually giving a shit about this, but I thought it might be useful to look at and see how the other side compares here. Here's kind of an example, right? So here you have diagram of architectures. So this is a vanilla transformer. So this is what we were looking at, right? You have this attention block, you have your residuals, and you have your feed forward. So that's exactly what we have here, right? We have our attention block, and then we have our feed forward, right? So that's our transformer. And then this is the mixture of experts, right, where you have the attention block, and then you have the 8 experts, right? So you would have 8 of these bricks, like side to side to side, and then the router network picks those. And then a Mamba is basically replacing that. So the selective state space model, what it replaces is these. But other than that, it's basically the same thing, right? It's you basically have these bricks that are repeating, you're feeding in sequences. It's a sequence-to-sequence model that outputs sequences and so on. And in MoE Mamba, they're basically just going to kind of do the same thing and have this mixture of experts here. And I assume they have a router as well. I'm not entirely sure. Let's see. A significantly improved transformer LLMs, including a recent state-of-the-art open source models. We propose to unlock the potentials of selective state space models for scaling, and they should be combined with MoE. We showcase this on Mamba, a recent SSM-based model that achieves remarkable transformer-like performance. Our model, MoE Mamba, outperforms both Mamba and Transformer MoE. In particular, an MoE Mamba reaches the same performance as Mamba in 2.2 less training steps, while preserving the inference performance gains of Mamba against the Transformer. So right off the bat, when you read an abstract like this, and the only thing that they have is that it's 2 times... It's not even... they're just basically saying it trains faster than the original one. Like, that's not... because people want to put their biggest results in the abstract. So if your abstract is like, hey, it's marginally faster than the previous paper, it's like, it's probably not going to be that great. But maybe just to talk about Mamba a little bit. So I found this paper or this blog post or something that basically describes what a Mamba is, and it's really, you could basically think of it like an RNN, right? Like a recurrent neural network. The idea in a recurrent neural network is that you basically have what's known as a hidden state, right? And the hidden state is basically packing all the information from the earlier part of your sequence, right? So if you think about what a transformer is doing, a transformer has this attention mechanism, and the attention mechanism is basically allowing any information from any previous part of the sequence to basically impact the selection of the next token, right? So that's both the blessing and the curse of the transformer, is that attention mechanism is quadratically scales with the length of the sequence, right? The reason it's a blessing is because you can pay attention to everything, right? Like any part of the sequence can impact any other part of the sequence, and that ends up being very powerful, right? Like not having any boundaries there ends up resulting in kind of more interesting behavior, and that's why transformers are basically the king. What a recurrent neural network does is it basically puts a cap on that. It says, okay, you're not going to be able to pay attention to every part of the sequence beforehand. What we're going to do is we're going to create something called a hidden state, and then we're going to basically put information that is important in that hidden state. And then whenever you want to determine the next token, you're not going to have access via an attention mechanism to every other part of the sequence. You're basically only going to be looking at this little hidden state, right? So the benefit of that is that dealing with the hidden state is going to be much faster, much more memory efficient, right? Because all you have to pass around is this little hidden state. But the negative of that is that there's just less way for information from way at the beginning of the sequence to really kind of like get in and impact what you're currently doing, right? So it's kind of like, you could think of it, if you wave your hands enough, kind of like what a convnet is doing, right? A convnet has a similar kind of idea in that it's basically limiting the region of space that certain features can kind of pay attention to, right? So the way that a convnet works is it kind of is limited to this particular little square, right? So that it's not really paying attention to the entire kind of global information. It's like limited in state space, right? Or limited in that space to just like a specific region, right? So like the receptive field is smaller. In a convnet, it's smaller because you like literally, that's just the way the architecture works. It's like literally you're just like only this part, everything there can kind of impact each other, and then so on. But in these recurrent neural networks, it's the state space that is kind of limiting in time. So you can kind of think of it like, obviously people who know RNNs and CNNs are probably cringing at the way that I'm describing this, but it's basically constraining the receptive field either in time or in space. But there was one thing in here that I thought was worth kind of pointing out. So in this article here, the key to this trick is the fact that RNNs are traditionally slow to train. And why are they slow to train is because you have to basically recreate this hidden state, right? So like if you want to push a gradient, now you can't just push a gradient and say, okay, well, everything that resulted in this output is basically the sequence itself, and it's all right here, right? It's all right here. There's no other part in this. Imagine if you had like a little arrow that went out this way, and it went to basically the hidden state, which the hidden state is basically coming out of the last time you performed inference on this. And then there's an arrow coming out of that, which is going to the time before that you performed inference on it, right? So the problem with these hidden states is that you basically have to constantly, it's really slow because you have to basically keep track of this hidden state. And then if you want to push gradients, now you're pushing gradients over a whole like time series of inferences. So since S4 is like the way the cool kids talk about selective state space models, I guess, can be run in convolutional mode or recurrent mode. So convolutional mode is, again, this idea where it's like kind of the same thing, but you're basically doing a convnet over time. So the reason Mamba is popular is because it can kind of be a convnet in training and an RNN for inference. So I hope that made sense. I feel like it doesn't make sense the way that I described it, but I don't know. Yerba Mate Fund, $20, dude. What? I appreciate it, Joseph Enox. I met these guys at a meeting with RWKV language model folks. Yeah, the RWKV is the same kind of idea, right? It's like basically all these transformer killers are basically just RNNs and CNNs or some combination of those two, right? It's like this, you're basically trying to get rid of this attention mechanism because the attention mechanism is what absolutely destroys your memory complexity and scaling. But the problem is that I think that that is literally the secret sauce. The reason transformers are so powerful is because they have basically no inductive biases, or the inductive bias that they have is that basically you don't get rid of any part of the sequence. Don't try to compress it. Don't try to have a forget gate and all this fancy like shit where you're kind of like adding information to this hidden state, removing information from this hidden state. Like just the whole sequence can interact with the whole sequence every single time. And I think that lack of that freedom allows interesting representations to emerge when you train for a massive amount of time on a massive data set, and that's why transformers are powerful. So I'm generally I don't feel like these RNN and CNN variants like RWKV and Mamba are necessarily gonna steal the throne, but I don't know, maybe they'll have some use case in like edge devices like phones or something like that. I don't know. Is there anything interesting here? These models can be seen as a combination of RNNs and CNNs. We have allowed SSMs to be scaled. Mamba allows linear time inference with respect to context length. Why is it linear? Because it doesn't matter, right? It doesn't matter if your context was 10 billion pages or if it was just one sentence. It's being reduced into this little hidden state. So no matter what, every time you perform inference, it's the same inference with the same size hidden state. You're never having to basically do this attention over the entire whatever the fuck was beforehand. Mamba mitigates the impact of the sequential nature of recurrence. I don't know. Doesn't get rid of it, though. Fusing GPU removes the requirement. Intermediate states are not saved, but instead recomputed. So they're doing some fancy shit here to try to prevent that. But I think the fundamental problem is that anytime you have this hidden state, you're basically removing information. You're losing information. Okay, so into the MoE part, which I think is probably the more relevant part for today. Two basic routing algorithms include token choice. Each token is routed to a constant number of experts k, and expert choice. The number of tokens is routed to each expert is constant across expert. Okay, so token choice means that it's kind of what they're doing here, right? It basically means that you're choosing, you have this router network which picks which experts to use and then routes it to those experts. So the token itself is determining which experts are choosing. You're picking the best experts for the token, right? Expert choice is saying, okay, well, actually, if you let the token pick, then you might end up with one expert that has to do all the tokens and another expert which has no tokens, right? Because the tokens are picking the most relevant expert that they want. If you do expert choice, you basically are saying each expert gets to say which of this batch of inference tokens that I need to predict are the ones that make the most sense for me as the expert, and then pick from that. And I guess that's a way to make sure that the number of tokens routed to each expert is constant across experts, if that was important, I guess. MoE models have found their way onto the open source scene. Although the underlying mechanism, Mamba retains the high-level block-based structure. In this paradigm, identical blocks comprising multiple layers are stacked one after another. The final value of the residual stream can subsequently be used to predict the next token in the large language model. Each layer's output being added to the residual stream. So this residual stream is this line coming in through here which is this line coming down through here. Right, and again, kind of what I was saying before, that's not something that you usually kind of think about, like, at least in the way that I always had it in my brain. I always thought the primary path was this, right? And then the residual pathway or skip connections were just kind of like little side paths like that. But it's like, it seems like this is kind of the more correct way to think about it, where the residual is the primary path, and then everything else is just kind of adding to that residual. See that? Adding the output of this to that, adding the output of this to that, adding the output of this to that. It's kind of like an interesting way to think about it, where the residual is the main path. The final value of the residual stream can subsequently be used to predict the next token. We leverage the compatibility of the two architectures. Every other Mamba layer is replaced with an MoE feed-forward layer based on switch. Interleaving Mamba layers with feed-forward layers results in a small decrease in performance compared to vanilla Mamba. So they're kind of like moving away from the Mamba anyways. The setup is denoted as Mamba MLP, right? Because it's not just a Mamba blocks, it's Mamba blocks with these feed-forward multi-layer perceptron mixture of experts. Separates unconditional. Okay. And that's basically it. It's basically just the Mamba with the mixture of experts block. Let's see if there's something here for the performance loss. Do we have like an actual benchmark? This is just the size. Parallel Mamba. Do we have any score here? This is fucking terrible. The only thing they're reporting is the loss. They're not even reporting like an eval. What the fuck? Okay, so we have no idea how good this model is. The only things they have here is like the loss, which is not indicative, right? Like your loss doesn't really mean anything. It does, right? Lower loss generally means you're going to have higher performance, but that's not telling me anything, right? Like you kind of want something like this. You want actual benchmarks where I can see the actual performance on some test. Okay. Holy shit, dude. Majetti with the 10. Damn, I don't know what to do, guys. It's you guys are showering me with gifts that I don't feel like I deserve, you know? I'm just some guy talking on the internet. All right. What do you guys want me to stall? I feel like I read through these papers. I don't know what to do now. Consecutive tokens are often assigned to the same experts. We observe some degree of positional locality in the pile dataset. The pile is basically a bunch of code. I wonder what it means that mixture of experts models perform much better in coding and math. Right? Like, what does that mean exactly, right? Like, if you look at this, look at the delta here in the performance of Mixtral 7B versus Mixtral 8x7B on math. That is really high, right? Same thing for code. You have this big delta. But for something like reasoning or comprehension, it doesn't really seem to be... Holy shit, dude. Arès Aurélien with Sec 100. I don't know what Sec 100 is. What is Sec? Sweden. It's Swedish krona. Pretty badass, dude. I didn't know you were from Sweden. But back to this. What? Right? Like, why do you have that? Why do you get much better performance if you have experts that decide when to do the indenting? right? Like this is math. So basically this and this drastically improves this row here, which is coding, and then this row here, which is math. These two tasks drastically improve with these experts versus this task down here, which is probably just like reasoning or something. It's like all text. Doesn't matter. This is so weird. Like, look at this. A model airplane, and then it's expert 1, expert 2, expert 2, expert 1. And here it's expert 1, expert 1, expert 2. This is like, it's almost like random. It's picking random experts. Which could be the case, right? Because if you have some kind of regularization that tries to force to use every expert equally, probably what ends up happening is that all of the experts might be able to do everything, right? So I feel like you need some kind of loss, something that pushes the experts to kind of specialize, right? Because it doesn't seem like these experts are specialists at all. So right, maybe that regularization that forces equal usage of the experts is like kind of handicapping this whole situation. Any thought on how MoE would be trained on function calling? So, I mean, you could train a language model to do function calling, and you could train a language model that uses MoE to do function calling. I don't think it would. I think it's like it's orthogonal. I don't think it necessarily matters. You could use. It might be better. I have no idea. Like maybe a Mixtral 7B, a Mixtral 8x7B performs better on whatever function calling benchmark you're interested in than a normal Llama 2 70B, you know? But it's hard to tell. I don't know. Right? Like think of it as function calling as basically just another thing here, right? Like you don't know whether it's going to look more like this, where it doesn't really matter, or whether it's going to look more like this. It could be like function calling is probably kind of more code and mathy, so it probably would perform way better. So yeah, maybe you could do that. They probably already have that, right? Function calling, Mixtral. Here you go, boom. This is a Mixtral 8x7B instruct fine-tuned for function calling with the same format as OpenAI. So here you go. If you guys have any code that uses the OpenAI function calling kind of calls, which I don't like, to be honest. Like the OpenAI function calling calls are like absolute dog shit. Like if we go to OpenAI docs, API reference here. Yeah, so you go to function calling. Where is it? Fine-tuning, chat, search, function calling. Here we go. Like this shit is so gross. Look at this. Type, function, name, description, parameters, type, property. Like, dude, what is this crap? I don't know. Generally, these type of specs like this, like the reason they're usually crap is because initially they're simple, right? Whenever they first come out, they're a pretty clean abstraction. But then over time, much like any other piece of software, you kind of had to add just a little extra thing, and then you add a little extra thing, and then you add a little extra thing, and then you add a little extra thing. And the next thing you know, your spec is just this giant tangle of shit that just is terrible. You know, but there's a benefit to that too, right? Because the more complicated your spec is, the more annoying it is to change, right? So this is like a secret sauce that some of these cloud providers do, right? Where let's say that you create your config to run your cloud on AWS, right? the more complicated AWS is and the more like annoying their spec is, the more likely it is that you're going to just continue using AWS, right? Because if you had to change it, then you're going to come to the conclusion that like, holy shit, I just spent all this effort. It's going to be so annoying. We're going to have to refactor all this stuff. Let's just stay with AWS, right? So there's kind of like a weird incentive there for cloud providers and API providers to have relatively complicated specs because they want you to stay in. They don't want you to change, right? But the kryptonite to that kind of thing is something like this, right? Where the guy's like, the function metadata format is the same. So if you were using OpenAI and all your code is written to do function calling like this, and you're tired of paying OpenAI a bunch of money for every API request, and then Sam Altman comes out and he makes it 10 times more expensive, because he wants to suddenly milk everybody for money, you can then always just come back here and use this one. So the wars. Boilerplate. Death by boilerplate. Okay, I feel like I'm wasting people's time. I'm just kind of talking about random shit, but let me summarize what we did today, and if you guys have any questions, hit me with the questions. Use GPTs to code for us. Let us forget about the mess. I agree with you. I see the writing on the wall, man, but I don't think coding is going to last much longer. I think we're very quickly moving into a world where you're still going to be coding, but it's going to be different. You're going to basically be coding with natural language. You're going to be like talking in English, and the computer will do all the coding for you, which, you could argue is already the case. Like, is Python a real programming language? Not really, like... I'm sure the people that were programming in the 80s and the 90s are like, dude, Python is fucking fake. It's just English. So now it's our turn to be those people, and we're going to look at the kids programming 10 years from now who are just like talking to a GPT, and the GPT is doing everything behind for them. And we're like, that's not real coding. All right. I'll stop stalling. Today, the stream was Mixtral 8x7B SMoE. Mixtral is a mixture of experts, and the original model is called Mixtral 7B. These are language models, and these come from a French company called Mixtral AI, which is everyone's favorite company because they basically released their model and the model weights with an Apache 2 license, which means you can use them in your products and startups. You can commercial use, research use. And it's basically the best open source model right now. So according to the chatbot arena, which I think is probably the strongest benchmark for language models, because it literally comes down to like the preference that people have for it. It basically is right up there with these proprietary models, and it beats out all the open source models. That doesn't necessarily mean it's going to stay there for very long. These benchmark or these leaderboards are going to change probably hundreds of times over the course of this year. As soon as GPT-5 comes out, there's going to be new models. Llama 3 is going to come out. Llama 4 might even come out this year. So like, these leaderboards are not set in stone. It's not entirely clear that a company that is this small can keep up with the race. It could be the case that they eventually get beat out by the kind of big incumbents, but so far, pretty good. What a mixture of experts is it's basically a standard transformer, except you're replacing the feed-forward block with this experts. And the experts are basically 8 feed-forward blocks. So here you have a transformer. Here's your multi-head attention, this brick here, multi-head attention. And then you have your feed-forward, or sometimes also called your MLP. That's this part here. So what a Mixtral model does is it basically takes this. So here you see how there's 3. That's because there's 3 heads. In the multi-head, there's 3 heads. Now imagine this, but 8 of them, right? So there's 8 of these in parallel. And then you have an additional little network here called the router network, which basically picks some subset of those 8 and then combines the output of those and then adds it to this residual. and so on. So you have basically for every feed forward block in your transformer, and there's going to be however many transformer blocks repeated, you're going to have basically 8 of these experts. So why do people do this? So the reason people do this is because it leads to better performance. It basically a mixture of experts model. Here, this yellow bar is better than this purple or this orange bar, which is the Mixtral 7B. The problem is that you pay for it. You pay for that extra performance with basically complexity and memory and compute. So Mixtral 8x7B is more complicated to run, and the inference is more complicated and takes more memory than something like the Mixtral 7B. And we looked at this paper here, which I recommend. It's a paper called Fast Inference of Mixture of Experts Language Models with Offloading. And in this paper, they basically try to get the Mixture of Experts model to run on consumer GPUs. And in consumer GPUs, you don't have a lot of VRAM, right? You don't have a lot of this GPU memory. And because of that, you end up in a very sticky situation where you basically have to be loading experts at runtime, where basically every time you can't load all the experts. So what you have is basically the experts are on the RAM, and you have to load them token by token, layer by layer at inference from the RAM into the VRAM, and that basically just destroys your inference speed. So in this paper, they basically quantize, so they quantize them to try to get them to fit into an even smaller amount, but that's not enough. So then they also basically create a LRU cache, a least recently used cache that tries to be a little bit intelligent. They have a little trick here where they basically look at the previous layer's residual states in order to try to predict and speculate on what the experts that they're going to need in the future are, and that allows them to basically preload these experts onto this LRU cache, and then in that way not have to wait for the CPU to go and load a specific expert at runtime. So they get a little bit of performance improvement from that, and this means that you can run a mixture of experts model on a small card such as an RTX 3060 or an RTX 3080, right? But the people at Mixtral don't really give a fuck about that because they're interested in kind of like big boy stuff, right? They have these batched inference servers that are sitting on these cloud server racks, right, where you have 8 nodes, and each of those 8 nodes can basically have a expert loaded. So you don't need to be doing this shit here where you're kind of loading an expert from your RAM. Basically, you have 8 GPUs. Each of the 8 GPUs has one of the experts loaded, which means that if you're getting a batch of requests, right, because you have 100 users kind of requesting, pinging your API at the same time, you can serve all of them, right? And the way that you kind of like allocate different experts to different tokens for each of your different users that has some other different use case, it all kind of works out, and you basically get a very efficient and fast inference speed and higher throughput for larger batch sizes. That's pretty much it. It's a cool little trick. You know, Mistral's a pretty hype company. Definitely looking forward to what they release in the future. And yeah, maybe as you guys suggested, there's probably cool stuff to be done with mixture of experts in other domains, right? You could probably have a mixture of experts in some kind of vision domain. I'm also thinking a mixture of experts for audio. You know, audio is a little bit more similar to LLMs, where you basically, it's like this kind of like 1D sequence. We know that distilling, I don't know if distillation has anything to do with this, but we know that audio generation seems to be pretty popular. Maybe you could do some kind of mixture of experts in the audio space there. I don't know what you would do, but I don't know, something there. Whisper. Mixture of experts whisper model. Maybe not. I feel like whisper already works pretty well. Like it's more about making it smaller, not necessarily more performant. And finally, we also kind of took a little detour to look at this paper, MoE Mamba, which was basically a MoE for these Mamba models, which are kind of like an RNN, CNN, right? They have this like hidden state that they keep passing along, but the problem with that is that that hidden state kind of loses information over time. So long term, I just don't feel like these SSMs are going to beat the transformers. I think the transformers are going to stay king for a little bit longer, but here they basically do it, and they don't really have good results in this one. All they said is it just trains a little bit faster and the loss goes lower, but you can't rely on the loss like that. You got to actually run evals to see if it's actually doing something, or whether, you know, it just figured out how to overfit better. But that's pretty much it, guys. Tomorrow, we're going to be doing more computer vision type stuff. So we're going to be looking at Gaussian splatting papers, specifically Langsplat, Compact 3D, amortized generative 3D Gaussians, spacetime Gaussians. If that's kind of more your jam, definitely join us tomorrow. If not, have a great weekend. Thanks, Eris. Thanks, Majetti. Thanks, Joseph, for the contributions. Thanks, everybody else, for all the comments and questions. 87GN, Black People. Your name is literally Black People. I'm sorry. Eleve Group, El Katie, Aris, Alejandro Rivas, some Chinese name that I can't read. Everybody else, Devashish Mishra, whatever. Thanks, everybody. Hope you guys have a great day. See you tomorrow. If not, see you guys later.